So in this paper, okay, oh, sorry. Wait. So in this paper, the authors doing the following research. The first is they interrogate the current meteorite barometer by evaluating their performance against large and compositionally diverse literature dataset of experimental meteorite compositions. The second is they adopt machine learning techniques to generate a novel single mineral meteorite barometer that is applicable to the full range of experimental meteorite compositions and is easily expandable, and subsequently apply this new barometer to the global data set of diamond-hosted meteorite inclusions to calculate their formation pressures. Okay, they mainly doing for those two aspects research. And then we talk about their data set. The data set has two parts. The first is experimental garnets. The composition in the data set comprise garnet from the experiment performed on bulk composition. And the second is the diamond inclusion. So, yeah. The second is diamond inclusion, the composition of diamond-hosted meteorites inclusions associated with sublithospheric regions were also collected from the literature. Then this table is about their data set. In this table, there are mainly composed of the content of major elements of meteorite and the atomic proportions per formula unit. And then the authors use evaluate the empirical barometer method using those data set, and 1, 2, 3, 4, those four figures corresponds to the four methods we mentioned before, and the x-axis is the predict pressure, and the y-axis is the measured pressures, and this line is one versus one line. We can see that this Beer's model produces the strongest statistical correlation between the experimental run conditions and the predict pressure with higher R square and the lower RMSE in those four figures. This is a summary of the empirical barometer. The first there's many contents, two drawbacks. The first is about the precision. From the figures we can know all appears to have an uncertainty at least plus or minus 5 GPa across all pressures, but they have a particular propensity to underestimate those from greater than 20 GPa. And the second drawback is they require some restrictions. They need the equilibration assemblage. But it's hard for the most natural diamonds. And given the above above reasons, authors use the machine learning method to establish a new barometer. And this table is a summary of measurement barometer from the previous study and compared with the performance of the machine learning in this study. And from this table, we can know the last one method, random forest regression, have the best performance with the highest R square and the lowest RMSE. And in the machine learning barometer, the target variable is pressure, and the dependent variable is those following elements, and they can get this future importance. From these figures, we can see the silicon and the sodium as the two most important compositional parameter, and which corresponds to the substitution mechanism. And then they apply this new barometer to the different region diamond, and this figure shows us the distribution of the practiced pressure, and the x-axis is predicted pressure, and the y is probability. And the distribution reveals that different locations have the diamonds from the distinct pressure environment, and we can look first at South African and the second South American inclusions, where the bulk of the global sublithospheric diamonds have been sampled. It can see that a significant greater percentage of the South African meteorite inclusion formed at the pressure shallower than the 10 GPa, or we can say the 300 kilometers depths, compared with very few similar inclusion found in the South American samples. Then look at other places. We can see almost most of them have the peak at the 10 GPa. Then there is some conclusions about this paper. Mainly the three aspects. The first is none of the available literature barometer reproduce the experimental pressure of organic varieties, or pressure estimates based on this empirical expressions could be incorrected by up to plus or minus 10 GPa based on the observed performance against the experimental data. The second, authors have adapted an active approach by using machine learning algorithm and experimental data set to treat meteorite barometer using random forest regression. The last one is applying this new barometer to the global database of diamond host inclusions reveals that their formation occurs in specific pressure models. Those about this paper. Then I'll talk something about diamonds of Bear's paper. Okay, before I start share this part, I want to talk about something diamond formation. Current models for the formation of natural diamonds involving the following three. Those three. The first is the reducing of the carbonate burning fluid or melt. by reacting with the reduced metal, like this equation. And the second is the oxidation of a methane burning fluid by reaction with the oxidized metal, like this equation. And the last one is the carbonate react with iron, like this equation. And we can say from those equations, we can say the formation of diamond will be associated with the oxidation state of metal rocks, which is likely controlled by the iron, ferrous iron, and ferric iron components in silicate minerals, metals, and melts. And the meteorite garnet, and we know meteorite garnet can host a significant ferric ion in its octahedral B side, even in the equilibrium with metallic ion. And so in the Bell's paper, they established the thermodynamic modeling for the incorporation of the ferric ion into the metal phases. That will allow us to make an estimate of the changing redox state in the Earth's metal. And I think Umi will introduce more details about this paper later on. And I just talk about something about diamonds, and we can and look at this figure. This figure also supports the meteorite compositions predicted by their aerodynamic model for a web-static ball composition, and they plot the composition of meteorite composition from the diamond inclusion from this place Jaggers 40, and the pressure for this, and the x-axis is pressure. The pressure for these samples are taken from the empirical barometer calculation of the bells, which we mentioned by the Thompson's paper. And we can see this three curves corresponds to the values at iron saturation, carbons, and carbonate saturation, where carbon is diamond. And we can see the agreement in major element chemistry is remarkable. And in this figure, look at this one. In this figure, those this figure convert is this right one, and this figure, in this figure, those support. We can say those diamond inclusions points generally lie between the iron saturated and carbon trade. Yes, is blue lines and orange lines. However, a couple of the inclusion have higher ferric ion contents, indicating the redox condition intermediate between the carbide and the carbonate saturation. Yes, like between the orange line and the green line. So this figure's results suggest that most of the sublicious fabric from this place, Jaggers 40 diamonds grew within the reducing float. So the Beers in the Beers paper, the authors get the result that meteorite inclusions are very powerful probe to characterize the diamond forming fluid. And this about the Bears paper. And that's all.
Okay, I think we'll move on with Umi. And then we're going to. Okay, thank you.
Okay.
Am I audible?
Yeah, yes.
Okay. Is my screen visible?
Yes.
Okay, so I'll just start with some basic background on the majorite and the sodium majorite substitution. So here we can see that this is the structural formula of the garnet, and here at a higher pressure condition, often the total number of silicon APFU, like atomic per formula unit of silica, it actually crosses the total value of 3. And apart from staying only in the tetrahedral site, silica also gets incorporated into the octahedral site. So this replacement generally occurs by these two kinds of substitution. And these are the majority and another N member, that is the majorite N member, that is mixed with this, that is incorporated into this garnet. So here what happens, this occurs by two different forms. So first is where in the B site itself, another 2+ ion, for example, like Fe or Mg. So the 2+ ions can get incorporated along with the silica ion, and therefore the 6+ charge will get balanced. So in this case, it is a majoritic substitution. And another type of substitution is where sodium is there, and these two sites are involved in the substitution, and another one single charged ion, that is sodium, is replaced. So this, like for example, sodium and silica replaces two of these ions. But this kind of substitution is mainly found in eclogitic rocks where sodium is abundant, and this is mostly dominated in case of peridotic rocks. So these are some plots that will possibly be a repetition of what Lee had said, but I'll just quickly go through it. So for this particular paper, Thompson, so when he compiled the data, he made some major plots where these are the total data set that he has plotted. And here what we can see is, like for example, magnesium. So here the legends are not given because they are so large in number. But the higher magnesium N members, they are from the peridotic rocks, and these lowers are generally from sedimentary rocks and all. And what he has done is, generally he had calculated the APFU, like atomic per formula unit, and only taken values where the total cation charge is between 7.9 and 8.1. The others have been removed, and the pressure range is about 6 to 25 GPa. And these majoritic and sodium majoritic, these two N members have been calculated using these formulas. And this is a similar plot, and these are the legends, of course. So what he has done is he has tried to plot these two kinds of substitutions. So these some points that are forming outside of these two vectors, because if these points that are within these two vectors, that means there have been a mixing of these two n member vectors, and both the replacement vectors have been operating. But the points that are falling outside of these vectors, that have been explained by like not the correct calculation of the ferric iron, because this ferric iron have been calculated based on the structural formula. And so in if there have been under assignment of the ferric ion, then these points can be placed outside these vectors. But we can see that most of the data points are on the vectors and some are within. So he has also, because most of the geothermobarometers that are constructed, they are not based on any rigorous thermodynamic models, but instead they are based on empirical formulas. So because they are constructed empirically, they mainly represent the structural cation that distribution. So in that case, they have tried to plot the pressure, the experimental pressure that they have got with the different parameters. For example, majoretic substitution, sodium majoretic substitution, or the tetrahedral and the octahedral trivalent, like the divalent cations and trivalent cations. So, we do not actually see much trend here. Only that similar kind of composition, they show similar kind of trend. So already these are the present barometers that already Lei had explained. So she already said about these equations. I'll not repeat them. And these are the criteria or the prerequisite condition that is required for application of these barometers. So first is the assemblage should be in equilibrium with clinopyroxene, and the second is it should not be in equilibrium with calcium perovskite. But the major problem is in case of diamond inclusions, these conditions cannot be met. And also if we see that when these pressure barometers are plotted, the samples that have a higher pressure range, for example, more than 20 or so, they are, you can see that they are not getting plotted on the 1:1 line. And these are mainly because these conditions are not being met, because they are not possibly in equilibrium, and these conditions, and they fall actually out of the calibration range. So therefore the R-square value is pretty low in all of the cases. And what they have tried to do is application of the machine learning methods. So the positive thing about machine learning is that we do not actually depend on the only particular factors. So here we can use the whole of the major composition, and they have used all these elements as a dependent variables, of course. So also this is because when we are making an empirical equation, we only we have some structural controls, and we try to focus only on that. For example, silicon, aluminum, iron. So we try to focus on these elements alone. But sometimes other elements, they also have some control on the incorporation of Fe3, like on the pressure. They also control the pressure, or they can be indicator of the pressure. So therefore, they have tried this method. Also, although the negative thing is we cannot have an equation. So we cannot actually judge like how the regression line is formed. So the goodness of it, we can see it is drastically improved in case of the random forest regression. And they have also tried the other kinds of regression. For example, the partial least square regression or principal component regression, but they do not show proper, they do not actually give a good result. Compared to that, random forest is fast and applicable at all pressures. So in case of random forest, they have constructed about 75 trees, and these are the three validation methods that they have tried. One is the KNN, another is the Monte Carlo 1000 times they've done Monte Carlo on a 70-30 ratio, and leave one out strategy. So these are the three validation methods that they have tried. So on the basis of that, these are the results that they have got. So when we see the factor dependence, so sodium, silica, aluminum, they have high values, which is expected because that is structurally controlled. But what is surprising is calcium and chromium, they show higher importance, like factor importance. So calcium and chromium, they actually show higher factor importance. So this is unexpected, and possibly there are some reason these two elements are controlling the pressure. So maybe this can be something that needs to be looked at. And the R2 score in this case has already been mentioned. It has drastically improved. But even then, in case of some these higher pressure values, there are some points that actually they are under, like when they're measured, they have like predicted pressure. So yeah, the predicted pressure is actually underreported, like it's lower than the measured pressure. So possibly these are the reasons that they have suggested. That one is the analysis of these data point, the like pressure analysis have been poor, or the experiments are not properly equilibrated, or the third is that maybe these higher n member points, they are underrepresented, or maybe this is just a drawback of the machine learning barometry. So anyways, even with all those drawbacks, it is clearly visible that this random forest barometry is far better than the other barometers that is used. And so these are the, so they have tried using different variables and have compared. So, and also they have tried to use it on the diamond intrusion that Lee had already mentioned, and they have tried to find out the pressure of the diamond intrusion, and they can see that they have actually been clustered at certain intervals. Like it's not a continuous graph, and the data they have, they are particularly they particularly show some certain pressures. So this is the Thompson paper. And the second one, that is on a similar topic, but the approach is a little different because they have tried experimentally to look at how this like pressure and iron concentration depends on each other. And they have found a reverse redox gradient. So these are the basic equations or the reactions that control the what do I say? The control the Fe3 plus the concentration in the mantle. So in the first reaction, what we can see is this is here the Fe2 plus iron is actually reduced, converted to Fe, the metal Fe and Fe3 plus, and this is because of a higher pressure condition. When the pressure gradually increases, the reaction generally moves towards right, and this pressure range is about 0 to 14 G. So, and the depth is about 180 to 700 kilometers. So here, in this case, the reaction moved rightwards. So these are some other reactions that control the ferric incorporation. And on basis of all of these, till a particular depth, it has been seen that with increase of pressure, the Fe3 plus by total Fe ratio gradually increases. And also, some people have found a positive correlation between calcium content and Fe3 plus by Fe. That is because of this particular reaction that occurs. That is already had shown this reaction. So in this paper, what they have done is they have tried to do this, show this experimentally, and they have taken this. These are the bulk composition that they have taken. So 2 mod composition, and these are the periodic composition. And this is basically more Fe-rich composition, which is more similar to the composition of Mars. So on basis of that, they have tried to do this experimentally. And so they have added 57 iron in some cases, so that the Mosby spectra that can be better quantified. And so here, these are the experimental conditions that have been used. So they have used these kind of buffers or capsules for that. And the different temperature and pressure have been used, almost ranging from 10 to 20 GPa. So this is the whole range of the pressure and temperature that have been used. And also to check whether, if what happens in case of an oxidized like melt. So here they have added oxygen, made it an oxygen enriched environment and tried to move the reaction backward. So in certain cases, they have tried this approach. And so this is a similar kind of majoritic and sodium majoritic substitution that have been used in the earlier paper. So, and these are the pressure and the Fe3 plus by Fe ratio that they have got after the result. So in certain cases, some examples, they are coming out of the range. So this is possibly, what they have said is these are the capsules that have leaked. There is a leak in the capsule. So these data they have not considered further. And they have measured the Fe3 plus by summation total Fe on like in two different methods. One is the Mosba method, one is the EELS in the temp. So because Mosba is more rigorous method, or it is more reliable method. So in most cases, they have tried to stick to the Mosba, and they also they have tried to regulate the parameters. Like in methodology, they have mentioned how they have tried to regulate the parameters so that in case of this EELS STEM method, the sample is not destroyed and they get the correct value. So they have also plotted it, and what they have seen is in higher Fe3 plus concentration, the EELS and Mosba data, they almost fit, like they almost follow on this 1:1 line. But at a lower concentration, that the iron concentration is highly over calculated in case of EELS. So mostly they have tried to use the Mosba method. And also apart from using this experimental method, what they have done is they have tried to model this this thermodynamically, and for that they have taken this this data set, and this data set is mostly on this NCF MASH system. And after running this thermodynamic model, what they have found out is experimental and the model results of Fe3 by total Fe, they give up like a considerable good fit, because they have taken very little, they have considered very little parameters, very less parameters. So even with so much less constraint, the result is good. So maybe if the experimental controls are like more experiments are done, so there is a high chance that it will give a better result. And so here they have compared the Fe3 plus by total iron and the pressure, and they have done it for these small points. They are the experimental data points, and these lines, they are basically they are the result of the model. So in case of this particular peridotite, what they have seen is in case of this reduced or reduced sample, this they give actually a good fit, and they are properly represented. In case of this basalt, there is we can also see that the pressure is actually, this iron concentration is very low, whereas according to the model it should have increased, but it doesn't. So they have tried to figure out what might be the reason. And in case of this Mars mantle as well, we can see that the experimental data points, they move downwards very quickly, whereas in case of model, the movement is very slow. So what they have said is possibly the size of the mineral, or the volume of the mineral that they have taken, that is possibly higher than the actual volume, and therefore the gradual drop in the ferric iron concentration is low in case of the model. But however, what the major observation is that till about 14 to 15 GPa, the redox reaction, that is the Fe3 plus by Fe total ratio, that gradually increases, and after that it again shows a reverse trend and it decreases. And this is all this has also been explained by some reactions, that because the olivine, that the structure of the olivine changes, and along with that the volume also changes. So after this 14 GPa, the del V value that was showing a negative change, that actually shows a positive change, and therefore the Fe3 plus by Fe concentration, that after 14 GPa, that again shows a reverse trend. So this is the carbon part that already Lei had explained. So that is all I had to say.
Okay, thank you, Wumi and Lei. Thank you both of you for the presentation. I just have a very small suggestion when people make the presentation, is that please don't copy and paste directly, trying to summarize, because all the information is included in the paper, and by presenting it, it just helps other participants to understand the paper. So it would be much better if you could avoid using too much words, but using some symbols or some key term to express the idea so that people will be more clear about it. But overall, it's pretty good. So everyone, so do you have any questions you would like to raise so that we can discuss? So Wumi, do you have any doubts about this paper?
Yeah, actually, I'm in some part, actually, I found it difficult to follow because this is not something like not really, I'm not accustomed to the equations and also. I think maybe I need to read up a little because.
Okay, so okay, then I have a question for you. So I think they use the model, like in Bayer paper, they use the model and the most power analysis to compare the results for the ferric iron to ratio. I don't think that fit is that good. I mean,
Yeah.
So do you think that the ferric iron model that you are working on, the machine learning model that you're working on, could improve on that?
Actually, I'm not sure because yeah, the fit of the machine learning model is better than what they have done in the Bayer paper. But again, I'm not sure that the reverse gradient that they have explained in Bayer. So how does that fit into the Thomson paper? Like they haven't considered that part. So they have done it based on the composition only. So does that affect it in some way?
Yeah, then that's another question. Actually, is that for Thomson paper, actually it's interesting. So they say 9 variables, 7 variables, and 5 variables. So basically, depending on how many features people choose, put in a machine learning model, it looks like they have very similar results, very similar performance. So, and also none of the features include ferric iron, as far as I could recall. So do you think do you think that ferric iron is important? But if their paper is right, then of course ferric iron. We have a very this is called, like, say, the upside and down of U shape.
Yeah, actually, if we include ferric iron in the Thomson paper, like the machine learning model, it will actually create problem in the model because after till 14 GPA it will behave in a certain way, and after 14 GPA it will behave in a different way. So that is possibly the reason in the model Fe concentration is not playing a role because it will actually not fit.
Okay. Okay, maybe that's one explanation for that. Okay. Okay, that makes some sense. Oh yeah, I have another question. And then for this 5 variables, 7 variables, and 9 variables that the Thomson paper choose. So what are those 5 variables? If my understanding is right, is that 5 variables, 7 variables, and 9 variables have shown very similar performance. That means some of the variables are dependent on each other. So if people do a heat map, looking at the correlations or Pearson coefficients of these different variables or different features, then we should be able to identify that which are independent variables, which are dependent pairs.
I think maybe they have used the relative importance as well, because here in the relative importance, what they have plotted is like 9 variables, and the important variables are actually 5, like SI, NA, AL, CA, CR. So these are actually 5 important variables that shows more than 0.1 importance. Maybe that is it. I am not sure.
Okay. That makes sense. Okay, that could also explain. But I don't know whether those 5, let's say, elements with a higher relative importance scores, whether those 5 elements, whether they are correlated with each other. I don't know.
They have done the PCR as well, like PC regression. They have done principal component regression. So maybe from there also they have got some idea. Maybe we can ask them, ask him in the presentation.
Yeah. You should ask. Yeah, please ask the question to the speaker. Okay. Okay. Anything else? Any other participants that have any questions? Okay, I have a question for Lei. Actually, I forgot what's the conclusion of Thompson. When he used a machine learning barometer, coordinate barometer, and applied that to global diamonds, he found that some of the deep diamonds, they are from the depth of what, 500 to 600 kilometers? Is that true? Because when Thompson applied his barometer, machine learning barometer, to the compositions and natural compositions of garnet, then it shows, actually I forgot the details. Then it shows that some of the diamonds, let's say, other than in South Africa and South America mainly is Huina, Brazil. In South America, there are a couple of places. So rather than these 2 places, for the rest of the garnets in the world, they all come from a depth of 300 kilometers. Is that right?
Yeah, actually, these figures show us the sublithospheric diamonds. So, there has other places all have the peak at the 10 GPa pressure, and almost from the more than about 3 kilometers depth. Yeah, it's mainly about the sublithospheric diamonds, I think.
Yes, but for South America and South Africa, so what is the other peak? It is a 17 GPa.
Yeah. Yep, they mostly in the Earth, super deep diamonds all comes from the South Africa. So I think there's a peak at South Africa is normally, yeah, and about
please share your slide. Please share your slide. Share your PPT.
Okay.
You share your screen.
Okay, wait.
Because I don't think that you answered my question. Yeah, please put that to that slide so that it will be clear.
Okay, wait.
Yeah, move back to the Thompson paper.
Yeah, and my screen is freezing.
Yes, it freezes.
Wait.
Okay, you could exit and then.
Okay. It's active?
Yes.
Okay. these figures.
Yeah. So actually, I forgot what he explained for 10 GPa. So my explanation, my understanding is that maybe 300 kilometers, let's say, is a lithosphere, a stellanosphere boundary. But the lithosphere does not always have 300 kilometers. That's too deep. And then here's another peak.
Yeah.
Here's another peak at about 17 GPa, right? For Southern Africa and South America, the second peak. I think.
Yeah. I think it's cause of the error of the machine learning models, and the authors also analysis that some natural garnets with some garnets within the meteorite have some CPX exclusion, and these models didn't have the consider the CPX exclusion, and so I think this is the error from this part.
Okay.
Yeah.
Okay. Maybe 10 GPa is not reliable. But
yeah.
I think what is interesting is that no matter whether it's right or not, if we whether it's that's a 10 GPa, maybe it's not 10 GPa in Earth's interior, because they didn't consider CPX exclusion here. But
yeah.
But it's interesting to see that they all have the similar peak. At least they are self-consistent with each other. I mean, other than Southern Africa and Brazil, other than these two places, the rest of the places that have the similar peak, actually, that's what makes me that feel it's very interesting. Okay, any other questions for other participants? Yeah, because for Thompson himself, in his 2016 paper in Nature, that's the highlight of his PhD work, that he used the carbonated periodized and then put at high pressure to look at the melting temperature. And it looks at that up to 25 GPa, the carbonated periodized has very low melting temperature. I forgot what's the exact temperature, maybe 1200 degrees C, something like that. Then he made the claim that for any of the subducted carbonated components, they could not enter the lower mantle because they are going to melt too easily because their melting temperature will be very low once it changes very high. Once it moves from upper mantle to the transition zone before it entering the deeper part of the lower mantle. And the reason for that is that the carbonate that they use is no longer the calcium magnesium carbonate anymore, because they use this because those pyroxenes, they are beginning to being absorbed by garnets with increase of depth. So the mineral composition evolved. So in the end, it is a very sodic and the sodium and the potassium rich pyroxene equilibrated with the carbonated pyrrhotite. Therefore, carbonates become very sodium potassium rich, and sodium and potassium carbonates has an extremely low melting temperature. That's why the carbonated, the sodium and the potassium rich carbonated pyrrhotite has a very low melting temperature at extremely high pressure. So that's the highlight of the Thompson's PhD work. And so this paper, basically in the discussion, he also talked about that, but I don't think the overall it has anything different, because people already know that some of deep diamonds come from really deep, but they are not from lower mantle. So that's not too surprising for me. And for the another paper, for Bayer paper, basically the continued process based on the previous people's work on mantle redox. So because for mantle redox, one way to calculate the mantle redox, if you only think about charge balance, so make it a charge really balanced, then it's most important to know the iron state, valence state, because iron has a elemental iron, iron 2+, and iron 3+. And since the iron in the primitive mantle has a concentration for about, let's say, 7 to 8% of iron. I mean, if you count as oxide, then that's about 10%. So the valence state of iron basically mainly determines the oxygen free gas in the Earth's mantle. So in upper mantle, shallow upper mantle, then ferric iron mainly resides in the spinel. Then deeper part, that's garnet, that was what Wumi is working on. And then if you go further deep, then that mainly resides in the perovskite. So people first find that in perovskite could host a lot of the ferric iron. So therefore, if the mantle would like to keep a charge balance, if the mantle, lower mantle has the same iron content as what we see in the upper mantle, then perovskite that holds too much ferric iron, so it needs some iron metal to equilibrate with that. Later on, that was first done by Dan Frost from University of Bayreuth in Germany. Later on, that was Robert when he was a PhD student at ETH, Switzerland, but he himself is a German. So he did the work and find that for garnet, majorite that in high pressure could host a lot of ferric iron. So basically, even in the deep upper mantle or in the transition zone, this garnet could host a lot of ferric iron, and therefore it also needs the saturation of iron, elemental iron, to make the charge balance. So for Bayer paper, basically he just did more work to look at that garnets, and they find that before people find that with increasing of pressure, the garnets could host more and more ferric iron. So basically iron 3+. But his work find that, okay, this only is true up to 14 GPa. Then once it's higher than 14 GPa, the garnets could not host more ferric iron. Basically, it actually hosts a little bit less ferric iron. So that's how he makes the claim. But I think that is very interesting when we read these two papers together, because as Wumi pointed out, that is probably one of the reasons why the Thompson paper, that for their relative importance, shows that iron is not that important. That's very likely the case, because it is not direct positive correlation with iron. Even with ferric iron, I don't think that is a positive correlation or simple correlation. Actually, it's complex. Okay, I think I've been talking a little too much. So, okay, you could stop sharing the screen. So Wumi, could you share some of the photos on your canvas?
Yeah. So is my screen visible? Hello?
Yes.
Yeah. So this is basically our main building for the IIT campus, and as you can see, it is actually located at a, like, it's not all building, it's actually a green campus. So and it has been raining a lot for the last few months actually. So now it is all clear, but these are the images of the rainy season. And this is actually outside our hostel. So, and the main locomotive that we students use are the cycles. So, and after, it's actually clear now. So, and this is outside, just outside our building. So, and also a new restaurant has opened, because most of the restaurants are closed due to COVID, and they just supply like they supply food, but they don't actually allow dine in. But one has opened inside the campus, and they have actually renovated. So that is the only place that we go to nowadays. So that is all I have to say.
Okay, thank you for sharing. Ulay, do you have any picture to share?
No.
Okay, that's okay. Okay, I think that's all about it. Thanks everybody for your participation, and thanks Lei and Wumi for leading the discussion. And on Wednesday, we're going to see the speaker giving a talk, and I think that we could ask him some questions. Yeah. Okay, that's all about it. Have a good evening, everybody. Bye-bye.